In this final chapter, we're going to look into optimizing digital systems to make them smaller, faster, higher performance, more energy efficient, and so on. It would be wonderful if we could achieve all these goals at the same time, and for some circuits we can. But in general, optimizing in one dimension usually means doing less well in another. In other words, there are design trade-offs to be made. Making trade-offs correctly requires that we have a clear understanding of our design goals for the system. Consider two different design teams. One is charged with building a high-end graphics card for gaming, the other with building the Apple Watch. The team building the graphics card is mostly concerned with performance, and within limits is willing to trade off cost and power consumption to achieve their performance goals. Graphics cards have a set size, so there's a high priority in making the system small enough to meet the required size, but there's little to be gained by making it smaller than that. The team building the watch has very different goals. Size and power consumption are critical, since it has to fit on a wrist and run all day without leaving scorch marks on the wearer's wrist. Suppose both teams are thinking about pipelining part of their logic for increased performance. Pipelining registers are an obvious additional cost. The overlapped execution and higher T-clock made possible by pipelining would increase the power consumption and the need to dissipate that power somehow. You can imagine the two teams might come to very different conclusions about the correct course of action. This chapter takes a look at some of the possible trade-offs. But as designers, you'll have to pick and choose which trade-offs are right for your design. This is the sort of design challenge on which good engineers thrive. Nothing is more satisfying than delivering more than anyone thought possible within the specified constraints. Our first optimization topic is power dissipation, where the usual goal is to either meet a certain power budget or to minimize power consumption while meeting all the other design targets. In CMOS circuits, there are several sources of power dissipation, some under our control, some not. Static power dissipation is power that is consumed even when the circuit is idle. In other words, no nodes are changing value. Using our simple switch model for the operation of MOSFETs, we'd expect CMOS circuits to have zero static power dissipation. And in the early days of CMOS, we came pretty close to meeting that ideal. But as the physical dimensions of the MOSFET have shrunk and the operating voltages have been lowered, there are two sources of static power dissipation in MOSFETs that have begun to loom large. We'll discuss the effects as they appear in N-channel MOSFETs, but keep in mind that they appear in P-channel MOSFETs too. The first effect depends on the thickness of the MOSFET's gate oxide, shown as the thin yellow layer in the MOSFET diagram on the left. In each new generation of integrated circuit technology, the thickness of this layer has shrunk as part of the general reduction in all the physical dimensions. The thinner insulating layer means stronger electrical fields that cause a deeper inversion layer that leads to NFETs that carry more current, producing faster gate speeds. Unfortunately, the layers are now thin enough that electrons can tunnel through the insulator, creating a small flow of current from the gate to the substrate. With billions of NFETs in a single circuit, even tiny currents can add up to non-negligible power drain. The second effect is caused by current flowing between the drain and source of an NFET that is, in theory, not conducting because VGS is less than the threshold voltage. Appropriately, this effect is called sub-threshold conduction and is exponentially related to VGS minus VTH, a negative value when the NFET is off. So as VTH has been reduced in each new generation of technology, VGS minus VTH is less negative, and the subthreshold conduction has increased. One fix has been to change the geometry of the NFET so the conducting channel is a tall, narrow fin with the gate terminal wrapped around three sides, sometimes referred to as a tri-gate configuration. This has reduced the subthreshold conduction by an order of magnitude or more, solving this particular problem for now. Neither of these effects is under the control of the system designer, except, of course, if they're free to choose an older manufacturing process. We mention them here so that you're aware that newer technologies often bring additional costs that then become part of the trade-off process. A designer does have some control over the The most straightforward way to improve performance is to reduce the propagation delay of a circuit. Let's look at a perennial performance bottleneck, the ripple carry adder. To fix it, we first have to figure out the path from inputs to outputs that has the largest propagation delay. In other words, the path that's determining the overall TPD. In this case, that path is the long carry chain following the carry in to carry out path through each full adder module. To trigger the path, add -1 and 1 by setting the A inputs to all 1s and the B input to all 0s except for the low order bit, which is 1. The final answer is 0, but notice that each full adder has to wait for the carry in from the previous stage before it produces 0 on its sum output and generates a carry out for the next full adder. The carry really does ripple through the circuit as each full adder in turn does its thing. The total propagation delay along this path is n-1 times the carry in to carry out delay of each full adder plus the delay to produce the final bit of the sum. How would the overall latency change if we, say, doubled the size of the operands? In other words, made n twice as large. It's useful to summarize the dependency of the latency on n using the order of notation to give us the big picture. Clearly, as n gets larger, the delay of the XOR gate at the end becomes less significant, so the order of notation ignores terms that are relatively less important as n grows. In this example, the latency is order n, which tells us that the latency would be expected to essentially double if we made n twice as large. The order of notation, which theoreticians call asymptotic analysis, tells us the term that would dominate the result as n grows. The yellow box contains the official definition, but an example might make it easier to understand what's happening. Suppose we want to characterize the growth in the value of the equation n squared plus 2n plus 3 as n gets larger. The dominant term is clearly n squared, and the value of our equation is bounded above and below by simple multiples of n squared, except for finitely many values of n. The lower bound is always true for n greater than or equal to 0. And in this case, the upper bound doesn't hold only for n equal to 0, 1, 2, or 3. For all other positive values of n, the upper inequality is true. So we'd say this equation was order n squared. There are actually two variants for the order of notation. We use the theta notation to indicate that g of n is bounded above and below by multiples of f of n. The big O notation is used when g of n is only bounded above by a multiple of f of n. Here's a first attempt at improving the latency of our addition circuit. The trouble with the ripple carry adder is that the high order bits have to wait for the carry in from the low order bits. Is there a way in which we can get the high half of the adder working in parallel with the low half? Suppose we wanted to build a 32-bit adder. Let's make two copies of the high 16 bits of the adder, one assuming the carry in from the low bits is 0, and the other assuming the carry in is 1. So now we have three 16-bit adders, all of which can operate in parallel on newly arriving A and B inputs. Once the 16-bit additions are complete, we can use the actual carryout from the low half to select the answer from the particular high half adder that used the matching carry-in value. This type of adder is appropriately named the carry select adder. The latency of this carry select adder is just a little more than the latency of a 16-bit ripple carry addition. This is approximately half the latency of the original 32-bit ripple carry adder. So at a cost of about 50% more circuitry, we've halved the latency. As a next step, we could apply the same strategy to halve the latency of the 16-bit adders, and then again to halve the latency of the 8-bit adders used in the previous step. At each step, we halve the adder latency and add a mux delay. After log base 2 of n steps, n will be 1, and we're done. At this point, the latency would be some constant cost to do a 1-bit addition, plus log base 2 of n times the mux latency to select the right answers. So the overall latency of the carry select adder is order log n. Note that log base 2 of n and log n only differ by a constant factor, so we ignore the base of the log in order of notation. The carry select adder shows a clear performance size trade-off available to the designer. Since adders play a big role in many digital systems, here's Here's another approach to improving the latency of our adder, this time focusing just on the carry logic. Early on in the course, we learned that by going from a chain of logic gates to a tree of logic gates, we could go from a linear latency to a logarithmic latency. Let's try to do that here. We'll start by rewriting the equations for the carry out from the full adder module. The final form of the rewritten equation has two terms. The G, or generate term, is true when the inputs will cause the module to generate a carry out right away without having to wait for the carry in to arrive. The P, or propagate term, is true if the module will generate a carry out only if there's a carry in. So there are only two ways to get a carry out from the module. It's either generated by the current module or the carry in is propagated from the previous module. Actually, it's usual to change the logic for the P term from A or B to A XOR B. This doesn't change the truth table for the carry out, but will allow us to express the sum output as P XOR carry in. Here's the schematic for the reorganized full adder module. The little summer product circuit for the carry out can be implemented using three 2-input NAND gates, which is a bit more compact than the implementation for the three product terms we suggested in Lab 2. Time to update your full adder circuit. Now consider two adjacent adder modules in a larger adder circuit. We'll use the label H to refer to the high order module and the label L to refer to the low order module. We can use the generate and propagate information from each of the modules to develop equations for the carry out from the pair of modules treated as a single block. We'll generate a carry out from the block when a carry out is generated by the H module, or when a carry out is generated by the L module and propagated by the H module. And we'll propagate the carry in through the block only if the L module propagates its carry in to the intermediate carry out, and H propagates that to the final carry out. So we have two simple equations requiring only a couple of logic gates to implement. Let's use these equations to build a generate propagate, or GP module, and hook it up to the H and L modules as shown. The G and P outputs of the GP module tell us under what conditions we'll get a carry out from the two individual modules treated as a single, larger block. We can use additional layers of GP modules to build a tree of logic that computes the generate and propagate logic for adders with any number of inputs. For an adder with n inputs, the tree will contain a total of n-1 GP modules and have a latency that's order log n. In the next step, we'll see how to use the generate and propagate information to quickly compute the carry-in for each of the original full adder modules. Once we're given the carry-in C0 for the low order bit, we can hierarchically compute the carry-in for each full adder module. Given the carry-in to a block of adders, we simply pass it along as the carry-in to the low half of the block. The carry-in for the high half of the block is computed using the generate and propagate information from the low half of the block. We can use these equations to build a C module and arrange the C modules in a tree as shown to use the C0 carry-in to hierarchically compute the carry-in to each layer of successively smaller blocks until we finally reach the full adder modules. For example, these equations show how C4 is computed from C0 and C6 is computed from C4. Again, the total propagation delay from the arrival of the C0 input to the carry-ins for each full adder is order log n. Notice that the GL and PL inputs to a particular C module are the same as two of the inputs to the GP module in the same position in the GP tree. We can combine the GP module and C module to form a single carry look-ahead module that passes generate and propagate information up the tree and carry in information down the tree. The schematic at the top shows how to wire up the tree of carry look-ahead modules. And now we get to the payoff for all this hard work. The combined propagation delay to hierarchically compute the generate and propagate information on the way up and the carry in information on the way down is order log n, which is then the latency for the entire adder, since computing the sum outputs only takes one additional XOR delay. This is a considerable improvement over the order n latency of the Ripple carry adder. One of the biggest and slowest circuits in an arithmetic and logic unit is the multiplier. We'll start by developing a straightforward implementation, and then, in the next section, look into trade-offs to make it either smaller or faster. Here's the multiplication operation for two unsigned 4-bit operands broken down into its component operations. This is exactly how we learned to do it in primary school. We take each digit of the multiplier, the B operand, and use our memorized multiplication tables to multiply it with each digit of the multiplicand, the A operand, dealing with any carries into the next column as we process the multiplicand right to left. The output from this step is called a partial product, and then we repeat the step for the remaining bits of the multiplier. Each partial product is shifted one digit to the left, reflecting the increasing weight of the multiplier digits. In our case, the digits are just single bits. In other words, they're 0 or 1. And the multiplication table is pretty simple. In fact, the 1-bit by 1-bit binary multiplication circuit is just a 2-input AND gate. And look, Mom, no carries. The partial products are n bits wide since there are no carries. If the multiplier has m bits, there will be m partial products. And when we add the partial products together, we'll get an n plus m bit result if we account for the possible carryout from the high order bit. The easy part of the multiplication is forming the partial products. It just requires some AND gates. The more expensive operation is adding together the m n-bit partial products. Here's the schematic for the combinational logic needed to implement the 4x4 multiplication, which would be easy to extend for larger multipliers, we'd need more rows, or larger multiplicands, we'd need more columns. The m times n 2-input AND gates compute the bits of the m partial products. The adder modules add the current row's partial product with the sum of the partial products from the earlier rows. Actually, there are two types of adder modules. The full adder is used when the modules need 3 inputs. The simpler half adder is used when only 2 inputs are needed. The longest pass through this circuit takes a moment to figure out. Information is always moving either down a row or left to the adjacent column. Since there are m rows, and in any particular row n columns, there are at most n plus m modules along any path from input to output. So the latency is order n, since m and n differ by just some constant factor. Since this is a combinational circuit, the throughput is just 1 over the latency, and the total amount of hardware is order n squared. In the next section, we'll investigate how to reduce the hardware costs, or separately, how to increase the throughput. But before we do that, let's take a moment to see how the circuit would change if the operands were 2's complement integers instead of unsigned integers. With a 2's complement multiplier and multiplicand, the high order bit of each has negative weight. So when adding together the partial products, we'll need to sign extend each of the n-bit partial products to the full n plus m bit width of the addition. This will ensure that a negative partial product is properly treated when doing the addition. And of course, since the higher order bit of the multiplier has a negative weight, we'd subtract instead of add the last partial product. Now for the clever bit. We'll add 1s to various of the columns and then subtract them later, with the goal of eliminating all the extra additions caused by the sign extension. We'll also rewrite the subtraction of the last partial product as first complementing the partial product and then adding 1. This is all a bit mysterious, but here in step 3, we see the effect of all the step 2 machinations. Let's look at the higher order bit of the first partial product, x3, y0. If that partial product is non-negative, x3, y0 is a 0, so all the sign extension bits are 0 and can be removed. The effect of adding 1 in that position is to simply complement x3, y0. On the other hand, if that partial product is negative, x3, y0 is 1, and all the sign extension bits are 1. Now when we add a 1 in that position, we complement the x3, y0 bit back to 0, but we also get a carry out. When that's added to the first sign extension bit, which is itself a 1, we get 0 with another carry out, and so on, with all the sign extension bits eventually getting flipped to 0 as the carry ripples to the end. Let's see if we can improve the throughput of the original combinational multiplier design. We'll use our patented pipelining process to divide the processing into stages with the expectation of achieving a smaller clock period and higher throughput. The number to beat is approximately one output every 2n, where n is the number of bits in each of the operands. Our first step is to draw a contour across all the outputs. This creates a one pipeline, which gets us started but doesn't improve the throughput. Let's add another contour dividing the computations in about half. If we're on the right track, we hope to see some improvement in the throughput. And indeed we do. The throughput is doubled. Yet both the before and after throughputs are order 1 over n. Is there any hope of a dramatically better throughput? The necessary insight is that as long as an entire row is inside a single pipeline stage, the latency of the stage will be order n, since we have to leave time for the n-bit ripple carry add to complete. There are several ways to tackle this problem. The technique illustrated here will be useful in our next task. In this schematic, we've redrawn the carry chains. Carryouts are still connected to a module one column to the left, but in this case, a module that's down a row. So all the additions that need to happen in a specific column still happen in that column. We've just reorganized which row does the adding. Let's pipeline this revised diagram, creating stages with approximately 2 modules worth of propagation delay. The horizontal contours now break the long carry chains, and the latency of each stage is now constant, independent of n. Note that we had to add order n extra rows to take care of propagating the carries all the way to the end. The extra circuitry is shown in the gray box. To achieve a latency that's independent of n in each stage, we'll need order n contours. This means the latency is constant, which in order of notation we write as order 1. But this means the clock period is now independent of n, as is the throughput. They are both order 1. With order n contours, there are order n pipeline stages, so the system latency is order n. The hardware cost is still order n squared. So the pipelined carry-save multiplier has dramatically better throughput than the original circuit. Another design trade-off we can remember for future use. We'll use the carry-save technique in our next optimization, which is to implement the multiplier using only order n hardware. This sequential multiplier design computes a single partial product in each step and adds it to the accumulating sum. It will take order n steps to perform the complete multiplication. In each step, the next bit of the multiplier, found in the low order bit of the B register, is ANDed with the multiplicand to form the next partial product. This is sent to the n-bit carry-save adder to be added to the accumulating sum in the P register. The value in the P register and the output of the adder are in carry-save format. This means there are 32 data bits, but in addition, 31 saved carries to be added to the appropriate column in the next cycle. The output of the carry-save adder is saved in the P register. Then, in preparation for the next step, both the P and B registers are shifted right 1 bit. So each cycle, 1 bit of the accumulated sum is retired to the B register, since it can no longer be affected by the remaining partial products. Think of it this way. Instead of shifting the partial products left to account for the weight of the current multiplier bit, we're shifting the accumulated sum right. The clock period needed for the sequential logic is quite small, and more importantly, is independent of n. Since there's no carry propagation, the latency of the carry-save adder is very small. In other words, only enough time for the operation of a single full adder module. After order n steps, we've generated the necessary partial products, but we'll need to continue for another order n steps to finish propagating the carries through the carry-save adder. But even at 2n steps, the overall latency of the multiplier is still order n. And at the end of 2n steps, we produce the answer in the P and B registers combined, so the throughput is order 1 over n. The big change is in the hardware cost at order n, a dramatic improvement over the order n squared hardware cost of the original combinational multiplier. This completes our little foray into multiplier designs. We've seen that with a little cleverness we can create designs with order 1 throughput, or designs with only order n. The discussion of design trade-offs completes part 1 of the course. We've covered a lot of ground in the last 8 lectures. We started by looking at the mathematics underlying information theory and used it to help evaluate various alternative ways of effectively using sequences of bits to encode information content. Then we turned our attention to adding carefully chosen redundancies to our encoding to ensure that we could detect and even correct errors that corrupted our bit-level encodings. Next, we learned how analog signaling accumulates errors as we added processing elements to our system. We solved the problem by using voltages digitally, choosing 2 ranges of voltages to encode the bit values 0 and 1. We had different signaling specifications for our outputs and inputs, adding noise margins to make our signaling more robust. Then we developed the static discipline for combinational devices, and were led to the conclusion that our devices had to be nonlinear and exhibit gains greater than 1. In our study of combinational logic, we first learned about the MOSFET, a voltage-controlled switch. We developed a technique for using MOSFETs to build CMOS combinational logic gates, which met all the criteria of the static discipline. Then we discussed systematic ways of synthesizing larger combinational circuits that could implement any functionality we could express in the form of a truth table. To be able to perform sequences of operations, we first developed a reliable bistable storage element based on a positive feedback loop. To ensure the storage elements worked correctly, we imposed the dynamic discipline, which required inputs to the storage elements to be stable just before and after the time the storage element was transitioned to memory mode. We introduced finite state machines as a useful abstraction for designing sequential logic. And then we figured out how to deal with asynchronous inputs in a way that minimized the chance of incorrect operation due to metastability. In the last 2 lectures, we developed latency and throughput as performance measures for digital systems and discussed ways of achieving maximum throughput under various constraints. We discussed how it's possible to make trade-offs to achieve goals of minimizing power dissipation and increasing performance through decreased latency or increased throughput. Phew! That's a lot of information in a short amount of time. Mr. Blue and the rest of the 6004X staff hope you found the course useful in increasing your skills in designing digital systems and analyzing their operation. You've completed several actual designs, and you're well on your way to designing a complete computer using our standard cell library. That's quite an accomplishment. If you'd like to continue the journey, please join us for part 2 of the course, where we'll discuss programmable architectures and work out the design of a modern 32-bit processor. See you then!